Look up at the night sky, and you'll see more than just stars. You'll glimpse the edges of a mystery that has haunted humanity since the dawn of time. The boundless cosmos stretches beyond our comprehension, a realm where distances are measured in light years, where black holes warp reality itself, and where galaxies spin like cosmic whirlpools in an ocean of darkness. This isn't just space, it's the greatest story ever told, written in the language of physics, light, and time. And yet, for all we've learned, the universe still holds secrets that defy explanation. What lies beyond the farthest galaxies we can see? How did it all begin? And where is it all heading? These aren't just scientific questions, they're deeply human ones, tugging at our curiosity like gravity pulling stardust into new worlds. Think about this. Every atom in your body was forged in the heart of a dying star. You are quite literally made of the cosmos. That connection between the vastness out there and the life right here is what makes exploring space so thrilling. It's not just about distant planets or swirling nebulae. It's about understanding our place in something unimaginably grand. For centuries, we've mapped the heavens with telescopes and equations, but each answer only reveals deeper mysteries. Take black holes, for example, regions where gravity is so strong, not even light can escape, or dark matter, an invisible force shaping the universe, yet completely undetectable to our instruments. These aren't just oddities, they're clues to a puzzle we're only beginning to solve. So let's set sail into the unknown together. In this video, we'll journey through the most mind-bending wonders of the cosmos, from the explosive births of stars to the eerie quiet of interstellar space. We'll unravel the theories that attempt to explain the unexplainable, and maybe, just maybe, catch a glimpse of what lies beyond the edges of our understanding. This isn't just a tour of the universe, it's an invitation to wonder, because when you stare into the depths of space, you're not just looking at the past, you're seeing the future of human discovery. Ready to dive in, the cosmos is waiting. To grasp the sheer enormity of the universe, let's start with something familiar: our home, Earth. Picture our planet as a tiny blue marble floating in an endless ocean of darkness. Now zoom out. The distance from Earth to the Sun, about 93 million miles, feels vast, but in cosmic terms, it's a mere stepping stone. That gap, known as an astronomical unit, is just the first stitch in a tapestry of unimaginable scale. Our entire solar system, with its planets, asteroids, and comets, spans billions of miles, yet it's still a speck compared to the Milky Way, a galaxy containing over 100 billion stars. Now imagine this: if the Milky Way were the size of a dinner plate, the observable universe would stretch farther than the distance between New York and Tokyo. That's right, 93 billion light-years of galaxies, each with billions of stars, woven into a web of cosmic structure. Even light, the fastest thing in existence, takes staggering amounts of time to cross these distances. The photons reaching your eyes from the Andromeda Galaxy, our nearest galactic neighbor, began their journey 2.5 million years ago, long before humans walked the Earth. But here's the humbling twist: everything we can see, from the faintest star to the most distant quasar, is just the observable universe. There's likely far more beyond what our telescopes can detect, realms hidden by the curvature of space-time or the limits of light's travel. Some theories suggest the true universe could be infinitely larger, a thought that bends the mind as surely as gravity bends starlight. So when you gaze up at the night sky, remember, you're not just looking at points of light. You're witnessing the edges of a mystery so vast, it redefines what it means to be small. 13.8 billion years ago, everything we know, every galaxy, star, and atom, was compressed into a singularity smaller than a single grain of sand. Then, in an incomprehensible flash, the Big Bang shattered that infinite density, unleashing space, time, and energy in a firestorm of creation. Picture it like a cosmic souffle, expanding faster than light itself in those first fleeting moments. Today, we see echoes of that explosion everywhere. The universe is still stretching outward, carrying galaxies along like raisins in rising bread dough. One of the most compelling pieces of evidence for the Big Bang is the cosmic microwave background radiation, a faint glow permeating the cosmos. This afterimage of the early universe, discovered by accident in 1965, is the oldest light we can observe. It's a snapshot of the universe when it was just 380,000 years old, a mist of particles cooling into existence. But there's something eerie about it. That radiation is nearly perfectly uniform, as if the entire cosmos was once small enough to reach thermal equilibrium before suddenly ballooning outward. Yet for all its explanatory power, the Big Bang Theory leaves us with dizzying questions. If the universe had a beginning, what triggered it? Some physicists speculate about a quantum fluctuation in a deeper, more fundamental reality, a random burp in the fabric of nothingness. Others propose cyclical models where universes expand, collapse, and rebirth in an endless loop. Then there's the multiverse hypothesis, suggesting our Big Bang was just one bubble in an infinite froth of parallel realities, each with its own laws of physics. Perhaps the most mind-bending thought of all, time itself may not have existed before the Big Bang. Our human intuition craves a before, but if space and time were born in that instant, the question might be as meaningless as asking what's north of the North Pole. The universe, it seems, is determined to keep its deepest secrets just out of reach for now. But with every telescope pointed skyward and every equation scribbled on a chalkboard, we're inching closer to understanding our spectacular, improbable origins. Here's a problem that keeps astrophysicists up at night. Nearly 85% of all matter in the universe is completely invisible to us. This is dark matter, the cosmic ghost that refuses to reveal itself, yet its gravitational fingerprints are everywhere. Imagine tossing a ball in an empty room, only to watch it suddenly curve midair as if tugged by unseen hands. That's essentially what's happening across the cosmos. Galaxies spin so fast that, by all known physics, they should fling themselves apart, yet something invisible holds them together with an unshakable grip. The hunt for dark matter began in the 1930s with Swiss astronomer Fritz Zwicky, who noticed galaxies in the Coma cluster moving far too quickly to be explained by visible matter alone. He called this missing mass Dunkel Materie, a dark matter, and the name stuck. Today, we know its influence is even more profound. Dark matter doesn't just bind galaxies, it sculpts the universe's very architecture. Vast filaments of it stretch between galaxies like cosmic spiderwebs, guiding where stars and gas collect over billions of years. Without it, the universe as we know it wouldn't exist. So how do you study something you can't see? Scientists have become cosmic detectives, piecing together clues through indirect methods. One brilliant trick is gravitational lensing. When light from distant galaxies passes through a dark matter cluster, its path bends like a car windshield, distorting the view ahead. By mapping these distortions, astronomers can literally weigh the invisible. Another approach involves particle colliders like the Large Hadron Collider, smashing atoms together at near light speeds in hopes of creating dark matter particles, hypothetical entities like WIMP, weakly interacting massive particles that might only whisper their existence through gravity. The wildest part, dark matter might not even be one thing. Some theories suggest it could be a mix of exotic particles, primordial black holes, or even flaws in the fabric of space-time itself. Each possibility opens doors to stranger realities like actions, particles so light they behave more like waves, or sterile neutrinos that barely interact with anything at all. Yet after decades of searching, dark matter remains elusive. Every null result from underground detectors or space telescopes deepens the mystery. Could we be missing something fundamental about gravity itself? Modified theories like modified Newtonian dynamics propose tweaking the laws of physics instead of invoking invisible matter, but most evidence still points to dark matter's existence. This isn't just academic curiosity. Solving the dark matter puzzle would rewrite the rules of particle physics, reshape our cosmic origin story, and maybe even reveal entirely new dimensions. Until then, it lingers as one of science's greatest riddles, a reminder that the universe, for all its splendor, still keeps its darkest secrets hidden in plain sight. If dark matter is the universe's invisible scaffolding, then dark energy is its mysterious engine, a force so baffling, it makes up 68% of everything in existence and is actively stretching the cosmos apart at an ever-increasing speed. Picture the universe as a loaf of raisin bread baking in an oven. The raisin's galaxies aren't just moving away from each other as the dough expands. The oven itself is getting hotter, pushing them apart faster and faster. That's dark energy in action, a repulsive force overpowering even gravity's relentless pull. The discovery of dark energy in the late 1990s sent shockwaves through astronomy. Two teams of researchers were studying distant supernova, expecting to find the universe's expansion slowing down due to gravity. Instead, they found the opposite. The expansion was accelerating, as if some unseen hand had pressed the cosmic gas pedal. This revelation earned them the Nobel Prize and left scientists scrambling to explain how space itself could behave this way. So what exactly is dark energy? The leading theory points to Einstein's cosmological constant, a term he originally inserted into his equations to keep the universe static, later calling it his greatest blunder when Edwin Hubble proved the universe was expanding. Yet now, it might be the key to understanding dark energy as an inherent property of space. Even in a perfect vacuum, empty space isn't truly empty. Quantum fluctuations suggest particles flicker in and out of existence constantly. Could these tiny bursts of energy be driving the universe apart? But there's a catch. When physicists calculate how much energy these quantum fluctuations should produce, the numbers are off by a factor of 1 followed by 120 zeros, a discrepancy so vast it's been called the worst prediction in the history of science. This leaves room for wilder ideas like quintessence, a dynamic energy field that changes over time, or even modifications to Einstein's theory of gravity itself. The implications are staggering. If dark energy continues unchecked, the universe could face a big rip, where galaxies, stars, and eventually atoms are torn apart by runaway expansion. Alternatively, dark energy might weaken or reverse, leading to a big crunch where everything collapses back into a singularity. Or perhaps it's just the first chapter in a cycle of universes, each with its own strange physics. For now, dark energy remains the ultimate cosmic wildcard, an invisible architect reshaping the fate of everything. As telescopes like the Vera Rubin Observatory and the Euclid Space Mission map the universe's expansion in unprecedented detail, we're inching closer to answers. But one thing's certain, the universe isn't just expanding, it's doing so with a momentum that defies everything we thought we knew. And that mystery might just be the most thrilling part of all. Black holes are the universe's ultimate paradox regions where gravity becomes so overwhelming, it twists the very rules of reality. Imagine a place where space and time swap roles, where the pull is so fierce that even light, traveling at 671 million miles per hour, can't break free. These cosmic monsters aren't just science fiction, they're real, and they're lurking in the darkness of space, reshaping everything around them. Most black holes begin with a spectacular death. When a massive star, at least 20 times heavier than our Sun, exhausts its nuclear fuel, it collapses under its own weight in a catastrophic explosion called a supernova. The outer layers blast away in a dazzling display, while the core crushes down into an infinitely dense point, a singularity. This is the birth of a stellar mass black hole, a gravitational trap with a boundary known as the event horizon. Cross this invisible line and there's no turning back, but black holes aren't all the same. Supermassive black holes, millions or even billions of times the mass of our Sun, sit at the centers of galaxies like cosmic anchors. How they grew so enormous remains a puzzle. Some might have formed from the direct collapse of giant gas clouds in the early universe, while others could have merged over eons, devouring stars and other black holes in their path. Then there's the strangeness that happens near the edge. Time slows down drastically due to gravitational time dilation. If you watched a clock fall into a black hole, its ticks would stretch longer and longer until they seemingly freeze at the event horizon, a haunting illusion for outside observers, while the clock itself plunges into oblivion. Meanwhile, tidal forces near smaller black holes would stretch you into a noodle-like strand in a process whimsically called spaghettification. In 2019, humanity captured the first direct image of a black hole's shadow, a glowing ring of hot gas swirling around the supermassive beast at the heart of galaxy Messier 87. This breakthrough, achieved by linking telescopes across Earth into a planet-sized observatory, confirmed predictions made by Einstein's theory of general relativity over a century ago. The image wasn't just a triumph of technology, it was a glimpse into the extreme physics governing these enigmatic objects, yet the true mystery lies beyond the event horizon. What happens inside a black hole? Some theories suggest the singularity isn't a point but a bridge, a wormhole tunneling to another universe or time. Others propose that black holes could be holograms with all their information encoded on their surfaces like a cosmic hard drive. There's even the wild idea that new universes bubble into existence inside them, birthing entirely separate realities with their own laws of physics. The study of black holes blurs the line between science and philosophy. They challenge our understanding of information, causality, and the nature of existence itself. As we peer deeper into their dark hearts, one thing becomes clear. Black holes aren't just destroyers, they're portals to the most profound questions the universe has to offer. And with every discovery, we're not just unraveling their secrets, we're rewriting the story of reality. If black holes are the universe's ultimate destroyers, neutron stars are its alchemists' cosmic laboratories where matter is crushed into forms so extreme, they defy the very laws of physics as we know them. Imagine taking the entire mass of our Sun and squeezing it into a sphere no wider than Manhattan. That's a neutron star, a remnant so dense that a single sugar cube-sized chunk of it would weigh more than Mount Everest. These stellar corpses are born from the violent deaths of massive stars, but unlike black holes, they don't vanish behind an event horizon. Instead, they become the universe's most bizarre timekeepers, magnets, and particle accelerators, all rolled into one. When a star between about 8 and 30 times the mass of our Sun explodes as a supernova, its core collapses inward with unimaginable force. Protons and electrons are smashed together so violently, they fuse into neutrons, hence the name. The result is a neutron star, a celestial object with a crust harder than diamond, floating atop an ocean of hyper-dense fluid that might behave like a superconductor or even a bizarre nuclear poster, where matter arranges itself into shapes resembling spaghetti or lasagna sheets under the crushing pressure. But the real magic happens when neutron stars start spinning. Some rotate hundreds of times per second, faster than a kitchen blender, becoming pulsars, cosmic lighthouses that sweep beams of radiation across space with metronomic precision. The first pulsar discovered in 1967 had such a regular signal that astronomers briefly nicknamed it LGM-1, short for Little Green Men, before realizing it was a natural phenomenon. Today, we use these cosmic clocks to test Einstein's theory of relativity, map the galaxy, and even navigate spacecraft with star-based GPS. Then there are magnetars, neutron stars with magnetic fields so strong they'd erase your credit cards from halfway across the solar system. These fields are a quadrillion times more powerful than Earth's, capable of twisting the star's crust and producing starquakes that release bursts of gamma rays, some of the brightest explosions in the universe since the Big Bang. In 2004, a magnetar flare 50,000 light-years away briefly ionized Earth's upper atmosphere, despite being far beyond our galaxy's edge. The most spectacular neutron star events are their collisions. When two of these ultra-dense objects spiral into each other, they don't just merge, they create ripples in space-time called gravitational waves, detectable by observatories like LIGO. These cosmic crashes forge gold, platinum, and other heavy elements, scattering them across the cosmos. That means the ring on your finger or the platinum in your phone might have been forged in the heart of a neutron star collision billions of years ago. Yet for all we've learned, neutron stars still guard profound mysteries. What lies at their cores? Some theories suggest quarks might break free from their neutron prisons, creating a soup of exotic particles. Others propose cores so dense they collapse into miniature black holes. There's even speculation about strange stars made of strange quark matter that could infect normal matter like a cosmic virus, converting entire stars into strange matter in a chain reaction. Neutron stars are more than just stellar curiosities, they're extreme physics experiments, nature's way of pushing matter to its absolute limits. By studying them, we're not just unraveling the fate of dead stars, we're probing the fundamental forces that shape reality itself. And every flash, every ripple, every pulse brings us closer to understanding the universe's most unforgiving environments, where gravity wins but curiosity refuses to surrender. For centuries, we wondered if planets existed beyond our solar system until the first exoplanet discovery in 1992 shattered that assumption. Today, we know of over 5,000 alien worlds, each rewriting the rules of what a planet can be. Picture scorching gas giants orbiting so close to their stars that their atmospheres evaporate into comet-like tails, or rogue planets drifting through interstellar space, untethered to any sun. But the real thrill lies in the handful of Earth-sized worlds nestled in the Goldilocks zone, that perfect distance where liquid water and perhaps life could exist. Finding these distant worlds is like spotting a firefly next to a searchlight. Astronomers use ingenious tricks to detect exoplanets indirectly. The transit method watches for tiny dips in a star's brightness as a planet crosses its face, a telltale shadow revealing the world's size and orbit. The radial velocity method tracks a star's subtle wobble, caused by an orbiting planet's gravitational tug. Then there's direct imaging, where advanced telescopes block out starlight to capture faint planetary glimmers, like photographing a candle beside a floodlight from miles away. Some discoveries defy imagination. Take Kepler 16b, a planet orbiting two stars like Luke Skywalker's Tatooine, or HD 189733b, where winds scream at 5,000 miles per hour, hurling molten glass sideways through its cobalt blue atmosphere. But the Holy Grail remains an Earth twin, a rocky world with water, an atmosphere, and just the right temperature. Planets like Kepler 452b, dubbed Earth's cousin, or the seven worlds orbiting TRAPPIST-1, a dim red dwarf, spark hope. 3 of them sit snugly in the habitable zone, though tidally locked with permanent daysides and nightsides. The next frontier, analyzing exoplanet atmospheres for biosignatures, gases like oxygen or methane that might hint at life. The James Webb Space Telescope is already sniffing out chemical fingerprints in alien skies. A whiff of unexpected compounds could rewrite biology itself. Yet, even if we find life, it might be unrecognizable organisms thriving in ammonia seas or breathing sulfur. This search isn't just about cataloging planets. It's a quest to answer humanity's oldest question: are we alone? Every new world discovered whispers possibilities, reminding us that Earth may be just one entry in a cosmic encyclopedia of life. And with telescopes growing more powerful by the decade, we might soon turn the page to a revelation that changes everything. The universe is unimaginably vast, with trillions of galaxies, each containing billions of stars. So where is everybody? That's the haunting question at the heart of the Fermi Paradox, named after physicist Enrico Fermi, who famously asked it during a lunchtime conversation in 1950. Given the sheer number of potential homes for life, the silence of the cosmos feels eerie, like walking into a party where the music's playing but no one's there. Statistically, civilizations should have arisen by now, leaving traces we could detect. Yet our telescopes hear nothing but cosmic static. One possibility is that life is extraordinarily rare. Maybe Earth hit a cosmic jackpot, a perfect storm of stable orbits, plate tectonics, and just the right ingredients to spark biology. Even if microbial life is common, the leap to intelligence might be vanishingly unlikely. Consider Earth. Life appeared quickly, but it took nearly 4 billion years for humans to evolve. Dinosaurs ruled for over 160 million years without developing technology. Intelligence isn't an inevitable outcome of evolution. It might be a fluke. Then there's the Great Filter Theory, a hypothetical barrier that prevents life from progressing to interstellar communication. The terrifying twist: the filter might lie ahead of us. If most civilizations destroy themselves before reaching the stars, through nuclear war, environmental collapse, or unchecked artificial intelligence, our own future could be bleak. Alternatively, the filter could be behind us. Something about abiogenesis or multicellular life might be astronomically improbable. But what if civilizations are out there, just staying silent? Advanced societies might hide deliberately, fearing predatory aliens, a concept called the dark forest hypothesis, where every civilization is a hunter in a cosmic jungle, terrified of revealing its location. Others might have moved beyond radio signals, communicating via neutrinos or quantum entanglement, technologies we can't yet detect. There's also the zoo hypothesis, the idea that aliens observe us like a nature preserve, avoiding contact to let humanity develop naturally. Or perhaps we're searching wrong. Our efforts focus on radio waves, but an advanced civilization might use methods beyond our comprehension, like manipulating space-time itself for communication. The vast distances between stars also play a role. Signals weaken over light years, and a conversation with even the nearest star system would take decades. By the time a message arrives, the sending civilization might be gone. The most unsettling answer: we might be alone. Earth could be the universe's first or only experiment in consciousness, a thought both humbling and profound. But with new telescopes scanning for technosignatures and biosignatures, we're closer than ever to solving the paradox. Whether the answer brings comfort or existential dread, one thing's certain: the silence of the stars is the greatest mystery we've ever faced. And the solution will rewrite not just science, but what it means to be human in a seemingly empty cosmos. Crossing the void between stars isn't just a technological hurdle, it's a battle against the very fabric of space and time. The nearest star system, Proxima Centauri, sits 4.2 light-years away. That's 25 trillion miles. With today's fastest spacecraft, the journey would take over 70,000 years. But humanity has never been content with impossible. From warp drives bending spacetime to solar sails riding sunlight, we're dreaming up ways to cheat the cosmic speed limit. Take the concept of a generation ship, a self-sustaining ark carrying multiple human generations across centuries. It sounds like science fiction, but the science checks out. Picture a city-sized vessel with farms, artificial gravity, and closed-loop ecosystems where descendants of the original crew would finally reach their destination. The challenges: maintaining social stability over generations, shielding against cosmic radiation, and avoiding micrometeoroid strikes over millennia. Even then, arriving at a potentially barren world raises ethical questions. Is it fair to doom countless generations to deep space for a gamble? Then there's propulsion. Chemical rockets won't cut it. We need breakthroughs like nuclear pulse propulsion, a wild idea from the 1950s that involves detonating atomic bombs behind a spacecraft to ride the shockwaves. Project Orion, as it was called, could theoretically reach 5% of light speed, cutting the trip to Proxima Centauri down to 80 years. The catch: launching nukes in Earth's atmosphere is, well, problematic. More refined concepts like fusion rockets or antimatter engines remain tantalizing but elusive, dependent on physics we've barely harnessed. Solar sails offer a quieter approach. These ultra-thin mirrors, kilometers wide, catch the momentum of photons streaming from stars. No fuel needed, just the gentle but relentless push of light. Japan's Ikaro's mission proved the tech works near Earth, and Breakthrough Starshot aims to miniaturize it, sending gram-scale probes with laser-pushed sails to Proxima Centauri in just 20 years. Scaling that up for human travelers, though, would require lasers with the power of a nuclear reactor and sails the size of continents, the Holy Grail. Warp drives, inspired by Einstein's general relativity, these hypothetical engines wouldn't move the ship, they'd warp spacetime itself, compressing the universe ahead and expanding it behind. Calculations by physicist Miguel Alcubierre suggest it's mathematically possible, but the energy costs are astronomical. Early estimates required the mass energy of Jupiter, though recent tweaks hint at more manageable scales. There's also the pesky issue of exotic matter with negative energy, a substance we're not even sure exists. Time dilation adds another layer of weirdness. At near light speeds, astronauts would experience time slower than those on Earth. A 20-year trip for the crew might mean centuries passing back home. Arriving at a star only to find Earth civilization unrecognizable is a haunting possibility. Interstellar travel isn't just about engineering, it's a mirror held to our ambitions, fears, and ingenuity. Every calculation, every prototype whispers the same truth: the stars aren't unreachable, they're just waiting for us to grow bold enough to bridge the gap. And when we do, it won't just be a leap for spacecraft, it'll be a leap for what it means to be human. What if everything you know, every star, every law of physics, every choice you've ever made, is just one version of reality among countless others? the multiverse theory isn't science fiction. It's a serious scientific hypothesis that suggests our universe might be a single bubble in an infinite cosmic froth, each with its own unique rules and histories. Imagine a library where every book tells a slightly different story of existence, some where gravity is stronger, others where life never emerged, or even realities where you made entirely different decisions. This isn't just a wild thought experiment. It's a frontier of cosmology that could redefine our place in the grand scheme of things. One version of the multiverse springs from cosmic inflation, the idea that our universe expanded exponentially in the first fractions of a second after the Big Bang. Some theories suggest this expansion never truly stopped. Instead, new pocket universes keep bubbling into existence, each with its own random combination of physical constants. In this scenario, our universe's finely tuned laws like the strength of gravity or the mass of an electron aren't miraculous. They're just a lucky roll of the dice in a cosmic casino where every possible outcome plays out somewhere. Then there's the many worlds interpretation of quantum mechanics, which proposes that every time a particle could go left or right, the universe splits into branches. Missed a bus this morning, somewhere, a version of you caught it. This isn't parallel worlds in distant dimensions, it's an infinite tree of possibilities growing from every quantum event, with trillions of new universes branching off each second. While it sounds like fantasy, this idea solves some of quantum theory's weirdest puzzles, like why particles seem to exist in multiple states until observed. String theory takes the multiverse even further, suggesting higher dimensional membranes, or brains, could float in a vast bulk space, occasionally colliding to create new Big Bangs. Picture soap bubbles bumping in a sink. Each collision could birth an entirely new universe with different dimensions. Some of these brains might be just millimeters away from us in a higher dimension, yet completely invisible to our three-dimensional perception. The implications are staggering. If the multiverse exists, it means every conceivable reality plays out somewhere, worlds where dinosaurs never went extinct, where the laws of physics allow for perpetual motion machines, or where life evolves in forms we can't even imagine. But how could we ever prove it? Some scientists hunt for bruises in the cosmic microwave background, anomalies that might show where our universe once bumped into another. Others look for evidence of shadow particles from neighboring brains. Critics argue the multiverse is untestable, slipping into philosophy rather than science. Yet its allure persists because it tackles profound questions. Why does our universe seem so finely tuned for life? Is there a deeper structure to reality we're only glimpsing? Whether the multiverse is real or not, the theory reminds us that the cosmos might be far stranger, richer, and more mysterious than we've dared to dream. And that possibility alone makes the search worthwhile. Time isn't the constant, unchanging river we perceive, it's more like a stretchy fabric, warped and woven by gravity and motion. This mind-bending truth comes straight from Einstein's theory of relativity, which revealed that time slows down near massive objects or when you're moving at incredible speeds. Picture two identical clocks, one placed on Earth's surface, the other launched into space aboard the International Space Station. After 6 months, the space clock will have ticked slightly slower, lagging behind by a fraction of a second. The astronauts living up there, they're technically aging slower than the rest of us, not by much, but enough for physics to take notice. This isn't just theoretical. GPS satellites orbiting 12,000 miles above Earth have to account for time dilation, or your navigation apps would lead you astray by kilometers. The satellites' clocks run faster than those on the ground because they experience weaker gravity, but they also move at 14,000 miles per hour, which slows time down. These opposing effects don't cancel out. relativity demands engineers tweak the satellite's timekeeping to stay accurate. Without these corrections, GPS would fail in minutes. The real shocker, time dilation, gets extreme near black holes or at near light speeds. Imagine a spaceship accelerating to 99% the speed of light. To the crew, a trip to a star 10 light-years away might feel like a few months, but back on Earth, decades would pass, a one-way ticket to the future. The same happens near a black hole's event horizon, where gravity's grip distorts time so severely that an outside observer would see you freeze in place, while you'd perceive your own time flowing normally. These effects force us to abandon the idea of universal now. Two events simultaneous for one observer might happen at different times for another, depending on their motion. It's as if the universe has infinite layers of time, each peeling away at different rates. This isn't science fiction, it's the bedrock of modern physics, confirmed by atomic clocks on jets, particle accelerators, and even the subtle time shifts between your head and feet due to Earth's gravity. What does this mean for the future? Interstellar travelers might return to an Earth centuries older than they remember. Colonies orbiting neutron stars would need calendars adjusted for extreme time warps. And if we ever harness near light speed travel, time dilation could become humanity's ultimate time machine, not by breaking the laws of physics, but by bending them to our will. The universe, it seems, doesn't just contain time, it plays with it, and understanding these rules might be the key to unlocking the stars. At the subatomic level, reality behaves like a cosmic magic trick. Particles pop in and out of existence. Electrons exist in multiple places at once, and objects separated by light years can instantaneously influence each other. This is the quantum realm, where the ordinary rules of physics dissolve into a haze of probabilities and paradoxes. Yet somehow, this bizarre micro-world shapes the vast cosmos we see through telescopes. The same quantum quirks that baffle scientists in lab experiments might hold the key to understanding black holes, the Big Bang, and the very fabric of space-time itself. Take superposition, the idea that particles like electrons don't have definite properties until measured. In a lab, we can trap an atom in a state where it's both spinning clockwise and counterclockwise simultaneously, like a coin perpetually flipping in midair. But scale this up and things get mind-bending. Some theories suggest the entire early universe existed in a quantum superposition, with every possible version of reality overlapping until something, perhaps the act of observation itself, forced it to choose one path. This could explain why our universe seems so finely tuned for life. Among infinite possible configurations, we simply ended up in the one where physics allowed galaxies, planets, and consciousness to emerge. Then there's quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, measuring one instantly determines the state of the other, no matter how far apart they are. This isn't just a lab curiosity, it might be how black holes communicate with their surroundings. The information swallowed by a black hole could be encoded in radiation at its edge, entangled with particles deep inside. Solving this puzzle could reveal whether information is truly lost in black holes or if it's somehow preserved, a dilemma at the heart of the black hole information paradox. But here's the cosmic headache: quantum mechanics and general relativity, our two most successful theories, refuse to play nice. Quantum physics thrives on uncertainty and probability, while Einstein's relativity paints a smooth, deterministic universe where gravity bends spacetime like a trampoline. Where they meet, like at the singularity inside a black hole or the first moments of the Big Bang, the math explodes into nonsense. Unifying them into a theory of quantum gravity is the holy grail of physics, and candidates like string theory and loop quantum gravity offer wildly different approaches. String theory imagines particles as tiny vibrating strings, with different notes corresponding to different forces and particles. It requires extra dimensions curled up so small we can't detect them, like an ant walking on a telephone wire that seems one-dimensional until you zoom in. Loop quantum gravity, meanwhile, suggests spacetime itself is woven from discrete loops, pixelating reality at the smallest scales. Both theories remain unproven, but they share a tantalizing idea that spacetime isn't fundamental, but emerges from something deeper, like temperature arising from the motion of atoms. The most promising testing ground for these ideas, the afterglow of the Big Bang. Tiny quantum fluctuations in the early universe stretched to cosmic scales, seeding the galaxies we see today. If spacetime is indeed granular, those fluctuations might carry fingerprints of quantum gravity, subtle imprints waiting to be spotted by next-generation telescopes. Other clues could come from lab experiments mimicking black hole conditions or detectors catching gravitons, the hypothetical particles carrying gravity's quantum force. Quantum mechanics doesn't just describe the universe, it might literally construct it. From the spark of virtual particles in empty space to the entangled webs stitching reality together, the quantum world whispers that the cosmos is far stranger, more interconnected, and more mysterious than we ever imagined. And in that strangeness lies our best shot at uncovering the universe's ultimate secrets. Deep in the cosmic shadows, something massive is pulling our entire galaxy, along with thousands of others toward it at 14 million miles per hour. Astronomers call this unseen force the Great Attractor, and despite decades of searching, its true identity remains one of the universe's most tantalizing secrets. Hidden behind the thick dust and stars of the Milky Way's galactic plane, this gravitational behemoth refuses to give up its mysteries easily. What could be yanking nearly 500,000 galaxies, including our own, through the void like cosmic marionettes? The first clues emerged in the 1970s when astronomers noticed something odd. Galaxies in our local supercluster weren't just drifting apart due to the universe's expansion. They were all streaming toward the same patch of sky near the constellations Centaurus and Hydra. Calculations suggested an incomprehensible mass, equivalent to tens of thousands of Milky Ways, lurked about 250 million light-years away. But when scientists pointed their telescopes in that direction, they hit a wall, literally. The Milky Way's dusty disk blocks visible light from that region, creating a celestial blind spot known as the zone of avoidance. Breakthroughs came when astronomers switched to wavelengths that pierce through dust like infrared and radio. Peering through the cosmic fog, they discovered the Norma cluster, a dense gathering of galaxies that might account for some of the Great Attractor's pull. But here's the twist, the math still doesn't add up. Even this massive cluster is too small to explain the staggering motion of galaxies. The real culprit might lie beyond it, something even more mind-bending. Enter the Laniakea supercluster, a filamentary web of galaxies spanning 500 million light-years, with the Great Attractor near its heart. Think of it as a cosmic watershed. Just as rivers flow toward the lowest point, galaxies are sliding down gravitational slopes toward this immense node. But Laniakea itself seems to be moving, tugged by an even larger structure, the Shapley supercluster, a staggering collection of galaxy clusters over 650 million light-years away. This raises a spine-tingling possibility. The Great Attractor might not be the final destination, but just a waypoint in an even grander cosmic flow. Could dark matter be the missing piece? Vast halos of this invisible substance are thought to envelop galaxy clusters, amplifying their gravity. If the Great Attractor sits at a knot in the cosmic web where dark matter concentrates, it might explain the extra pull. Or perhaps there's something stranger, a primordial flaw in spacetime, a collision of parallel universes, or even a relic from before the Big Bang. The hunt continues with tools like the James Webb Space Telescope and next-generation radio arrays, peeling back the Milky Way's dusty veil. Every new map of this hidden realm brings us closer to understanding not just the Great Attractor, but the architecture of the universe itself. One thing's certain, whatever's out there, it's rewriting the story of how our cosmos moves and where we're all headed. Among the universe's most elusive relics are cosmic strings, hypothetical threads thinner than a proton but denser than a mountain range, woven into the fabric of space-time itself. Picture cracks frozen in the cosmic ice of the early universe, formed during the fiery chaos moments after the Big Bang, when fundamental forces were still separating. These aren't mere cosmic curiosities, they're potential time capsules carrying imprints of the universe's infancy and clues to physics we've yet to imagine. The theory behind cosmic strings springs from phase transitions in the early cosmos, like water freezing into ice, but on a universal scale. As the newborn universe cooled, imperfections might have formed in the geometry of spacetime, creating ultra-thin filaments of concentrated energy. These strings wouldn't just sit still. Simulations suggest they'd vibrate at near light speeds, snapping and recoiling like invisible whips. A single cosmic string stretching across the observable universe could weigh as much as a galaxy, yet its width would be smaller than an atom, a paradox of density that defies everyday intuition. What makes them so tantalizing? For starters, their gravitational influence could explain odd wrinkles in the cosmic microwave background, subtle temperature variations that current models struggle to account for. Some astronomers even speculate that cosmic strings might create double images of distant galaxies, bending light around themselves like ghostly lenses. But the wildest possibility, their loops could warp spacetime so severely that they'd form closed time-like curves, theoretical pathways allowing time travel to the past. While this remains speculative, the mere idea thrusts cosmic strings from abstract physics into the realm of science fiction's grandest dreams. Detecting them, however, is a cosmic needle in a haystack challenge. Unlike black holes or neutron stars, strings wouldn't emit light or radiation, just faint gravitational ripples as they oscillate. Observatories like LIGO and future space-based detectors might catch these whispers, but there's another clue. If a string slices through space, it could leave a telltale jump in the sky, a sudden shift in the position of stars on either side of its path. Imagine the night sky subtly torn along an invisible seam, revealing the string's presence for a fleeting moment before spacetime heals itself. The hunt for cosmic strings isn't just about proving their existence. It's a quest to test grand unified theories, which attempt to merge all fundamental forces. If strings are real, their properties could reveal energies 1 trillion times beyond what particle colliders can reach, offering a glimpse into the universe's first trillionth of a second. They might even connect to string theory's multidimensional brains, suggesting our universe is just one thread in a vast cosmic tapestry. For now, cosmic strings remain ghosts in the equations, a tantalizing what if at the edge of known physics. But if we ever find them, they won't just rewrite textbooks, they'll unravel the very fabric of reality, showing us that the universe is stranger, more intricate, and more wondrous than we dared to suspect. And that discovery could be waiting in the next glimmer of starlight, the next ripple in space-time, or the next anomaly in the cosmic microwave background's silent song. If black holes are the universe's ultimate one-way streets, white holes would be their bizarre opposites, cosmic fire hydrants blasting out matter and energy with no way back in. These hypothetical objects emerge straight from Einstein's equations of general relativity, mathematically valid solutions that flip black hole physics on its head. While black holes devour anything crossing their event horizons, white holes would violently repel everything, spewing light and particles into space like a celestial fountain stuck in permanent eruption. But here's the catch: no one's ever seen one, and their existence would shatter some of physics' most cherished rules. So why do scientists even entertain such a wild idea? The concept first gained traction in the 1960s when physicists realized Einstein's field equations were symmetrical, meaning every black hole solution had a theoretical twin running backward in time. Picture a black hole's collapse in reverse. Instead of a dying star imploding into a singularity, a white hole would explode outward from one, hurling material into the universe like a big bang in miniature. Some theories even suggest white holes could be the other end of black holes, connected by wormholes in a cosmic subway system. Toss a rock into a black hole here, and it might come flying out of a white hole light years away, assuming you could survive the trip through a tunnel crushed by unimaginable gravity. But there's a glaring problem with white holes. They violate the second law of thermodynamics, which states entropy or disorder always increases. A white hole's endless expulsion of organized energy would effectively reverse entropy, like unscrambling an egg or unburning a log. That's why many physicists dismiss them as mathematical ghosts, artifacts of equations divorced from reality. Yet, intriguingly, certain phenomena in our universe do resemble white holes. Gamma-ray bursts, the most energetic explosion since the Big Bang, eject jets of matter at near light speed with no clear source. Some theorists speculate these could be white hole echoes, fleeting glimpses of physics operating beyond our current models. The most radical idea: white holes might not exist in the present universe at all, but could represent the final fate of black holes. In the quantum realm, black holes aren't eternal prisons. They slowly leak radiation over eons, a process discovered by Stephen Hawking. Some models suggest that when a black hole fully evaporates, it doesn't vanish. It rebounds as a white hole in a spectacular finale. If true, the cosmos could be littered with primordial black holes from the early universe, now quietly detonating as white holes in distant voids, their fireworks too faint for our telescopes to catch. Whether cosmic reality or mathematical mirage, white holes force us to confront the limits of our understanding. They remind us that the universe, for all its apparent order, might harbor phenomena that defy intuition, where time runs backward, entropy reverses, and the fabric of space itself unravels into new possibilities. And that's exactly why they're worth chasing, even if they remain forever out of reach, because sometimes the most outrageous ideas light the path to the deepest truths. What if everything you see, the stars, planets, even your own hands, is nothing more than an incredibly convincing illusion? The holographic principle proposes exactly that. Our three-dimensional universe might be a projection from a two-dimensional surface, like a cosmic movie screen encoding reality at its edges. This isn't science fiction. It's a serious theory born from the clash between quantum mechanics and black hole physics, suggesting that space itself could be a grand deception. The idea first gained traction in the 1990s when physicists grappling with black holes stumbled upon a paradox. When matter falls into a black hole, what happens to the information it carries? Quantum mechanics insists information can't be destroyed, yet black holes seemingly erase it. The solution: the information isn't lost. It's smeared across the black hole's event horizon like data etched onto a celestial hard drive. This revelation led to a jaw-dropping realization. The three-dimensional volume inside a black hole might be entirely encoded on its two-dimensional surface. Scale this up and the entire universe could work the same way. Think of it like a holographic credit card sticker. At first glance, the image appears three-dimensional but tilted, and you'll see it's just flat foil with patterns that create the illusion of depth. Similarly, the holographic principle suggests that every particle, every force, every event in our universe might be pixels on a vast, two-dimensional surface at the edge of reality. Your morning coffee, the Andromeda Galaxy, even the thoughts in your brain, all could be shadows cast by interactions on this distant boundary. But how could this possibly be true? The math hinges on a concept called entropy, a measure of disorder. Black holes have entropy proportional to their surface area, not their volume, implying that all the information inside them is somehow stored on their outer shell. If the universe has similar rules, then the cosmos might be a projection, with every cubic light-year of space deriving from bits encoded on a flat surface we can't perceive. The implications are staggering. If the holographic principle holds, it would mean the universe operates like a quantum computer, with space-time itself emerging from entangled quantum bits on a two-dimensional plane. This could solve long-standing puzzles, like why gravity is so weak compared to other forces. It might not be a fundamental force at all, but a side effect of deeper information processing. Even time could be an emergent property, a cosmic sleight of hand tricking us into perceiving a flowing reality. Critics argue the theory is untestable, but experiments are underway. Fermilab's holometer searched for quantum fuzziness in space-time tiny fluctuations that might betray its pixelated nature. Future gravitational wave detectors could hunt for holographic noise, faint ripples revealing the universe's true two-dimensional skeleton. Even the cosmic microwave background might hide patterns pointing to a holographic origin. Whether the universe is truly a hologram remains unknown, but the principle's real power lies in its audacity. It forces us to question the very nature of reality, to consider that space and time might not be fundamental, but emergent like the glow of a screen creating the illusion of a world. And if that's true, then the greatest magic trick isn't happening in some distant galaxy. It's happening right here, in every atom, in every thought, in the very fabric of existence itself. Imagine a civilization so advanced it doesn't just harness the energy of a planet, it commands the output of entire stars, bending galaxies to its will. This isn't science fiction, it's the Kardashev Scale, a mind-bending framework that sorts civilizations by their energy mastery. Proposed by Soviet astronomer Nikolai Kardashev in 1964, this scale starts humbly with Type 1, a society that fully utilizes its home planet's resources, controlling weather, geothermal energy, and even sunlight. Humanity, we're not even on the board yet, hovering around Type 0.7, still tethered to fossil fuels and baby steps in solar tech, but the scale quickly ascends into the extraordinary. A Type 2 civilization doesn't just use energy, it builds around it. Picture a Dyson sphere, a megastructure enveloping a star to siphon its entire output. For perspective, capturing just 1% of our sun's energy would meet current human demand 10 trillion times over. A Type 2 society might also move stars themselves, rearranging cosmic neighborhoods for optimal energy harvesting. And then there's Type 3, where the word limit loses meaning. These beings would tap into the power of multiple galaxies, wielding energy on scales that make supernova look like firecrackers. The eerie part, if such civilizations exist, we might not recognize them. Their technology could resemble natural phenomena like quasars blinking in coded patterns or dark matter structures too vast for our telescopes to pass. Some theorists argue that advanced societies might even transcend physical energy entirely, storing consciousness in quantum fields or manipulating space-time itself. That's the scale's brilliance. It doesn't just measure energy use, it hints at how intelligence could reshape reality. So where are all the Type 3s? Fermi's paradox looms large here. If the universe is billions of years old, why haven't we detected cosmic construction projects or galaxy-spanning beacons? One chilling answer may be civilizations hit an evolutionary wall, a great filter before reaching Type 1. Climate collapse, AI gone rogue, or self-destructive wars could snuff out progress. Alternatively, advanced beings might eschew expansion, opting for digital utopias inside simulated realities, leaving the physical universe quiet. Yet the Kardashev Scale isn't just about aliens, it's a mirror for humanity's potential. Reaching Type 1 would mean uniting as a planetary civilization, no small feat amid our divisions. But the stakes are cosmic. Master clean fusion, asteroid mining, or space-based solar, and we're on the path. Stumble, and we risk joining the silent graveyard of failed civilizations. Either way, the scale reminds us that intelligence isn't just about thinking, it's about doing, transforming energy into something grander than survival. And in that transformation, we might just find our place among the stars. What if life on Earth didn't actually begin here? The theory of Panspermia suggests that the seeds of biology might have hitched a ride across the cosmos, arriving on our planet via asteroids, comets, or even interstellar dust. Picture this: billions of years ago, a rogue space rock carrying microscopic organisms or their molecular blueprints could have crashed into our young planet, sparking the chain of events that led to us. It's a wild idea, but the evidence isn't as far-fetched as it sounds. Take the Murchison meteorite, a space rock that landed in Australia in 1969. Inside, scientists found amino acids, the building blocks of proteins, along with nucleobases, key components of DNA and RNA. These weren't just random chemicals, they were the same organic molecules that form the foundation of life on Earth. Even more intriguing, some of these compounds had structures unlike anything found naturally on our planet, hinting they were forged in the cold, radiation-drenched depths of space. But how could life survive such a journey? Space is a brutal place. After all, freezing temperatures, lethal radiation, and the vacuum itself should shred delicate organic material. Yet extremophiles, Earth's toughest microbes, have shown us otherwise. Bacteria like Deinococcus radiodurans can withstand radiation doses thousands of times stronger than what would kill a human, while tardigrades, tiny water bears, have survived the vacuum of space in experiments. Freeze-dried and dormant, these organisms could theoretically endure millennia-long trips inside meteorites, awakening when they reach a hospitable world. The most compelling twist: panspermia might not even require intact organisms. Complex organic molecules, like those found on comets such as 67P Churyumov-Gerasimenko, could act as cosmic starter kits, delivering the raw ingredients for life to planets with the right conditions. Imagine a young Earth as a sterile kitchen, waiting for a meteorite to drop off the first batch of groceries. Of course, panspermia doesn't answer how life first arose, it just shifts the mystery elsewhere in the universe. But that's what makes it so thrilling. If true, we might all be descendants of interstellar travelers, our ancestry written not just in Earth's rocks, but in the chemistry of distant nebulae and the icy hearts of comets. And if life can hop between worlds, then every planet, moon, or even rogue asteroid drifting between stars could be a potential oasis, waiting for the right spark to awaken. The implications ripple outward. If life is a cosmic inevitability rather than a local accident, the universe could be teeming with biology we've yet to meet. Missions like Europa Clipper and Mars Sample Return could soon test this idea, hunting for microbes or their remnants in our solar system's icy moons and red deserts. Finding even a single extraterrestrial organism with DNA resembling ours would be a smoking gun, proof that we're not just Earthlings, but citizens of a far grander, interconnected biosphere. Panspermia blurs the line between here and out there, suggesting that life isn't confined to planets. It's a traveler, a survivor, and perhaps a shared inheritance across the stars. Whether it's true or not, the theory reminds us that our story might not be Earth's alone. It could be written in the dust of supernova, carried on solar winds, and waiting, even now, to take root somewhere new. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a burst of radio waves so powerful and unusual that the astronomer reviewing the data circled it in red ink and scribbled, "Wow." Next to the signal, that simple exclamation gave the phenomenon its name, and nearly 50 years later, the wow signal remains one of the most electrifying and unresolved mysteries in the hunt for extraterrestrial intelligence. For 72 seconds, the Big Ear telescope at Ohio State University locked onto a narrowband radio emission coming from the constellation Sagittarius, a frequency matching the predicted signature of an artificial interstellar transmission. It was 30 times stronger than the background noise of space, and it vanished just as suddenly as it appeared, never repeating despite decades of follow-up scans. What made this signal so compelling wasn't just its intensity, it was its frequency. The wow signal pulsed at 1420 MHz, a quiet spot on the radio spectrum where cosmic noise is minimal, and where scientists had theorized an advanced civilization might deliberately broadcast. This frequency also happens to be absorbed by water and hydroxyl molecules, leading some to speculate it could be a cosmic hello designed to signal life-friendly worlds. But here's the puzzle. Natural cosmic phenomena like pulsars or comets don't produce such focused, short-duration signals at this frequency. Even the most exotic astrophysical explanations fall short. The leading natural theory points to hydrogen clouds or a passing comet, but the evidence is shaky. In 2017, researchers suggested comet 266P Christensen, which happened to be in the area at the time, might have reflected Earth's own radio transmissions. Yet the comet's position didn't align perfectly with the signal's origin, and the reflected signal wouldn't explain the wow signal's unique characteristics. Another idea involves a rogue microlensing event, where a distant star's light was briefly magnified by an invisible object, creating a transient radio flare. But these events are vanishingly rare, and none have ever matched the wow signal's profile. Then there's the tantalizing possibility, the one that sends shivers down the spine, that we caught a fleeting whisper from another civilization. Imagine a directed beacon sweeping across the galaxy like a lighthouse beam, momentarily illuminating Earth before spinning away into the void. If so, the signal's one-time nature makes tragic sense. An alien transmission would take years to reach us, and by the time we turned our telescopes toward its source, the sending civilization might have long since moved on or gone silent. Despite countless searches, including a dedicated effort in 2012 using the vastly more powerful Allen telescope array, the wow signal has never been detected again. Its ephemeral nature only deepens the intrigue. Was it a cosmic fluke, a glitch in our instruments, or the closest we've ever come to proof that we're not alone, until another signal like it appears, or until we uncover a definitive natural explanation? This 72-second burst will linger as both a triumph and a torment, a reminder that the universe might be shouting at us in a language we're only beginning to decipher. And somewhere out there, just maybe, someone else is listening too. In October 2017, astronomers spotted something extraordinary, a visitor from beyond our solar system, tumbling through space at nearly 200,000 miles per hour. Named Oumuamua, Hawaiian for scout or messenger, this strange object defied every expectation. Unlike the icy comets or rocky asteroids we're familiar with, Oumuamua resembled a cosmic cigar, stretching nearly a quarter-mile long but only a tenth as wide, spinning chaotically as it raced past the sun. Its trajectory was bizarre too. Instead of slowing down as expected after swinging by the sun, it inexplicably sped up, as if propelled by some unseen force. Theories exploded almost as fast as Oumuamua itself. Some scientists proposed it was a rare type of hydrogen iceberg, evaporating in sunlight and creating a natural thrust. Others suggested it might be a fragment of a shredded planet, ejected from another star system eons ago. But the most tantalizing hypothesis came from Harvard astrophysicist Avi Loeb, who argued Oumuamua's acceleration and unusual shape could hint at an artificial origin, perhaps a light sail from an advanced civilization drifting between the stars. What made Oumuamua so puzzling wasn't just its behavior, it was how little time we had to study it. By the time telescopes spotted it, the object was already speeding away, leaving astronomers scrambling to capture every possible scrap of data. Its surface, oddly reflective and possibly metallic, didn't shed gas or dust like a typical comet, and its tumbling motion suggested a violent past, maybe a collision that sent it careening toward us. The debate over Oumuamua's true nature reveals a humbling truth. We're still beginners in the study of interstellar objects. For centuries, we assumed everything in our solar system was homegrown, but Oumuamua proved the cosmos is constantly exchanging material across vast distances. Since its discovery, we've spotted at least one more interstellar visitor comet, Borisov, in 2019, but none as enigmatic as that first cosmic scout. Whether Oumuamua was a weirdly shaped space rock or something more extraordinary, its brief visit changed astronomy forever. It forced us to reconsider what might be sailing through the void between stars, unseen until it streaks through our neighborhood. Future telescopes like the Vera Rubin Observatory will scan the skies for more of these interstellar nomads, hoping to catch the next one before it's gone. Because one thing's certain, the universe has more surprises waiting, and they might already be on their way. Back in 1961, astronomer Frank Drake scribbled a simple equation on a chalkboard, a formula that would become the backbone of the search for extraterrestrial intelligence. The Drake equation isn't your typical math problem with a neat solution. Instead, it's a thought experiment, a way to quantify our cosmic loneliness, or lack thereof, by breaking down the vast unknowns of the galaxy into manageable pieces. At first glance, it looks deceptively straightforward. Multiply the rate of star formation by the fraction of stars with planets, then by the number of habitable worlds per system, and so on, until you arrive at an estimate of civilizations capable of communicating across the stars. But peel back the layers and you'll find each variable is a rabbit hole of its own, revealing just how much we still don't know about life's place in the universe. Take the first factor, the rate of star formation. Our galaxy churns out roughly 7 new stars per year, but how many of these are stable, long-lived suns like ours? Red dwarfs, the most common stars, might host planets but bathe them in deadly flares. Then there's the fraction of stars with planetary systems. Just 30 years ago, we weren't sure if other stars even had planets. Now, thanks to missions like Kepler, we know planets outnumber stars, with billions of Earth-sized worlds orbiting in the habitable zones of their suns. That's the easy part. The equation's next terms how many of those planets develop life, and how often life evolves intelligence, plunge us into speculation. Life arose quickly on Earth, but did it do so against astronomical odds? And intelligence isn't inevitable. dinosaurs ruled for eons without inventing radio telescopes. The final variables are the real wild cards. How long do civilizations last? A sobering thought lurks here. If technological societies tend to self-destruct within centuries, the galaxy might be littered with silent ruins. Estimates using the Drake equation swing wildly from a lonely one, us, to millions of chatty civilizations. The range isn't a flaw, it's a reflection of our ignorance. Every new exoplanet discovery, every breakthrough in astrobiology tweaks the numbers. For instance, the recent detection of phosphine in Venus's clouds. A potential biosignature suggests life might thrive in places we never considered, nudging the odds upward. The equation's brilliance lies in its framing. It doesn't just guess at alien civilizations, it forces us to confront the gaps in our knowledge. Why haven't we found anyone yet? Maybe we're overestimating how long civilizations survive, or perhaps we're searching wrong, like sailors scanning the ocean for smoke signals while submarines glide silently beneath. Programs like SETI have spent decades listening for radio waves, but an advanced civilization might use lasers, neutrinos, or something we haven't imagined. The Drake equation reminds us that the universe isn't just a place, it's a story, and we're still learning how to read it. So where does that leave us? The equation isn't a calculator, it's a conversation starter, a cosmic mirror reflecting both our curiosity and our limitations. With every telescope pointed skyward and every lab simulating the origins of life, we're not just solving for n, the number of civilizations. We're asking a deeper question. In a galaxy that could be teeming with life or eerily empty, what does it mean to be the ones doing the asking? The answer, for now, is written in the stars and in the spaces between the numbers we're still learning to fill. Gamma-ray bursts are the universe's ultimate fireworks, blinding flashes of energy so intense, they outshine entire galaxies for a few fleeting seconds. In that brief instant, a single burst can unleash more power than our sun will produce over its entire 10 billion-year lifespan. These cosmic detonations come in two flavors: short bursts, lasting less than 2 seconds and thought to be caused by neutron stars colliding in a catastrophic embrace, and long bursts, which stretch for minutes and signal the death throes of massive stars collapsing into black holes. Either way, the violence is almost incomprehensible. A typical burst beams energy in narrow jets, moving at 99.99% the speed of light, carrying enough force to vaporize a planet instantly if caught in their crosshairs. The first gamma-ray burst was detected accidentally in 1967 by U.S. military satellites designed to watch for nuclear tests. What they found instead was a pulse of radiation so powerful, it briefly blinded their instruments. For decades, astronomers debated whether these bursts originated in our galaxy or from the far reaches of the cosmos. The mystery was solved in 1997 when the Bepo-SAX satellite pinpointed a burst's afterglow, revealing it came from a galaxy billions of light-years away. That's when the true scale of their power became clear. These weren't just explosions. They were universe-shaking events visible across unfathomable distances. What makes them so deadly? The energy in a gamma-ray burst isn't just raw power. It's packed into photons 1,000,000 times more energetic than visible light. If one occurred within a few thousand light-years of Earth, the radiation would strip away our ozone layer, bathe the planet in lethal UV rays, and potentially trigger mass extinctions. Some scientists even suspect a gamma-ray burst might have contributed to the Ordovician extinction 450 million years ago, wiping out 85% of marine life. The good news: the chances of a nearby burst are slim. Most occur in distant galaxies, and the Milky Way's structure makes a direct hit unlikely. But the risk, however small, is a humbling reminder that we exist at the mercy of cosmic forces beyond our control. Yet these explosions aren't just agents of destruction, they're also cosmic forges. The same collisions that create short gamma-ray bursts are thought to produce heavy elements like gold and platinum, scattering them across the universe. Every time you see a gold ring, you might be looking at stardust forged in a neutron star collision billions of years ago. And for astronomers, bursts serve as flashlights in the dark, their afterglows illuminating the earliest epochs of the universe. The most distant burst ever detected, GRB 090423, erupted just 630 million years after the Big Bang, offering a glimpse into an era when the first stars were still flickering to life. The study of gamma-ray bursts is a race against time. Satellites like NASA's Swift and Fermi telescopes scan the skies around the clock, alerting ground-based observatories within seconds of a burst detection. By the time you finish this sentence, another burst might have already flared and faded in some distant galaxy, unseen by human eyes. But with each one we catch, we're piecing together the life cycles of stars, the birth of black holes, and the extreme physics that govern the universe's most violent moments. They remind us that for all its beauty, the cosmos runs on a scale of energy and time that dwarfs human experience, a reality both terrifying and awe-inspiring. Cosmic inflation is one of the most radical ideas in modern cosmology, a moment when the infant universe didn't just expand, but exploded in size faster than the speed of light, stretching from smaller than an atom to the size of a grapefruit in less than a trillionth of a second. Picture blowing up a balloon to the size of Earth, then inflating it to the scale of the observable universe almost instantly. That's the breathtaking scale of inflation, a theory proposed in the 1980s to solve some of the Big Bang's biggest puzzles. Take the universe's eerie uniformity. No matter which direction we point our telescopes, the cosmic microwave background, the afterglow of the Big Bang, shows nearly identical temperatures across billions of light years. Without inflation, regions of space now on opposite sides of the sky would never have had time to reach thermal equilibrium. It's like walking into a room where two cups of coffee, placed miles apart, have cooled to the exact same temperature without ever being near each other. Inflation solves this by suggesting these regions were once pressed together before being flung apart faster than light could keep up, preserving their initial conditions like a snapshot frozen in time. But what could power such an expansion? The leading theory points to a mysterious field called the inflaton, a kind of cosmic fuel that briefly dominated the universe's energy. As this field decayed, it released a staggering amount of energy, reheating the universe into the hot, dense plasma we recognize as the Big Bang's aftermath. Think of it as a cosmic reset button. Inflation smoothed and stretched space, then its end ignited the familiar particles and forces we see today. The evidence for inflation is compelling but indirect. Tiny quantum fluctuations in the inflaton field were stretched to cosmic scales, creating minuscule density variations that later seeded galaxies and galaxy clusters. These fluctuations left their fingerprints in the cosmic microwave background, matching predictions with stunning precision. Yet inflation isn't without its critics. Some argue it's too flexible, able to explain almost any observation by tweaking parameters. Others propose rival ideas, like a bouncing universe that avoids a singularity altogether. The wildest implication, inflation might still be happening. Most of the universe stopped inflating after that first fraction of a second, but some theories suggest pockets of space could continue expanding exponentially, spawning endless bubble universes with different physical laws. Our entire cosmos might be one such bubble in an infinite multiverse, a humbling thought that redefines our place in reality. Whether inflation is the final answer or a stepping stone to deeper truths, it reshaped our understanding of the universe's birth. It turns the Big Bang from a singular event into a cosmic crescendo, an explosion of space itself, setting the stage for everything that followed. And somewhere in those first fleeting moments, the seeds of galaxies, stars, and life itself were sown, stretched across the void by forces we're only beginning to comprehend. The cosmic microwave background, that faint glow left over from the Big Bang, is supposed to be the universe's fingerprint, a nearly uniform tapestry of temperature variations no larger than a few millionths of a degree. But in 2005, astronomers studying data from NASA's WMAP satellite stumbled upon something unsettling, a series of unexpected alignments in the radiation's fluctuations, as if the universe had subtly tilted its head in one particular direction. Dubbed the axis of evil by scientists partly for its unnerving implications, partly for its uncanny alignment with the ecliptic plane of our solar system, this anomaly defies one of cosmology's most cherished principles, that the universe should look the same in all directions, with no preferred axis or special vantage point. At first glance, the patterns seem innocuous, slight asymmetries in how hot and cold spots are distributed across the sky. But when researchers ran the numbers, the probability of such alignments occurring by chance was less than 1 in 1,000. It's like rolling a die 100 times and getting the same number suspiciously often, not impossible, but enough to make you question whether the die is weighted. Some theorists argue it's just a cosmic coincidence, a trick of perspective or incomplete data. Others worry it hints at something deeper, a flaw in our understanding of the early universe, or even evidence of a pre-Big Bang structure imprinting itself on reality. One controversial explanation suggests the axis might be a relic of inflation, the universe's explosive early growth spurt. If inflation wasn't perfectly uniform, if space stretched slightly more in one direction than another, it could have left behind a faint directional bias frozen into the cosmic microwave background. Another, even wilder idea posits that our universe isn't entirely isolated, that the axis could be a gravitational bruise from a collision with another universe in the multiverse, like a fingerprint pressed into clay. Then there's the unsettling possibility that we're seeing something far more mundane, contamination from our own solar system, dust in the ecliptic plane, the magnetic pull of nearby galaxies, or even the way we process the data could introduce subtle biases. The Planck satellite, which mapped the cosmic microwave background with unparalleled precision, confirmed the anomaly but couldn't settle the debate. The axis persists, taunting cosmologists with its refusal to fit neatly into the standard model. What makes this more than just an academic curiosity is what's at stake, the foundation of modern cosmology. If the universe truly has a preferred direction, it would upend the Copernican principle, the idea that Earth, and by extension humanity, holds no special place in the cosmos. It would mean the universe isn't just subtly lopsided, it might be fundamentally stranger than we thought. Until the next generation of telescopes or a breakthrough in theory cracks the case, the axis of evil remains one of the universe's most provocative puzzles. A whisper that the cosmos might still be keeping secrets from us, written in the oldest light there is. What if the universe around you, the stars, the trees, even the device you're holding right now, isn't actually real? Simulation theory proposes exactly that. Our entire reality might be an intricate digital construct, an artificial universe running on some unfathomably advanced computer built by a civilization far beyond our own. It sounds like the plot of a sci-fi movie, but this idea has gained surprising traction among scientists, philosophers, and even tech billionaires. The core argument is startlingly simple. If a civilization could create simulations indistinguishable from reality, and if they chose to run countless such simulations, the statistical likelihood that we're in the original universe becomes vanishingly small. Think of it like video games. A century ago, the most advanced graphics were stick figures on a cathode ray tube. Today, we have photorealistic virtual worlds populated by AI-driven characters. Extrapolate that progress 1,000 or 1,000,000 years, and it's not hard to imagine simulations so perfect, their inhabitants, potentially conscious beings like us, would never suspect they weren't real. This is the essence of philosopher Nick Bostrom's famous trilemma. Either advanced civilizations never reach the capability to create such simulations, they universally choose not to, or we're almost certainly living in one. Given the absence of evidence for the first two options, the third becomes uncomfortably plausible. The implications ripple outward. If we're in a simulation, the laws of physics might not be fundamental truths, but programmed parameters, arbitrary rules set by the simulators. Glitches in this cosmic code could explain quantum mechanics weirdness, like particles existing in multiple states until observed. Even the speed of light might just be a processing limit, the universe's equivalent of a frame rate. Some theorists suggest searching for these glitches, like tiny pixel-like irregularities in the fabric of space-time or mathematical patterns hidden in cosmic constants. Others propose that black holes could be cosmic garbage collectors, deleting unneeded data to conserve processing power. But here's the twist: the simulation hypothesis might be unfalsifiable. Any evidence we uncover could itself be part of the simulation. This leads to wild philosophical debates about consciousness. If we're simulated, are our thoughts and emotions real, or just elaborate lines of code? And who's to say there aren't simulations within simulations, nested realities like Russian dolls? Critics dismiss the idea as modern solipsism, arguing it's no more provable than the existence of an invisible dragon in your garage. Yet the theory persists because it forces us to confront profound questions. What is reality if not what we perceive? And if we're just data in some higher being's hard drive, does that make the universe any less wondrous? After all, whether rendered in atoms or algorithms, the awe we feel when we look at the night sky is undeniably real to us. And that, perhaps, is the simulation's most haunting beauty. It reminds us that reality, however constructed, is something we experience, not just observe. Time travel isn't just the stuff of science fiction. It's already happening, just not in the way you might expect. Thanks to Einstein's theory of relativity, we know that time isn't a fixed, universal clock ticking at the same rate for everyone. Instead, it's more like a river flowing at different speeds depending on how fast you're moving or how close you are to a massive object. This means that, in a very real sense, traveling to the future is not only possible, it's been experimentally proven. Take astronauts aboard the International Space Station, for example. Because they're orbiting Earth at over 17,000 miles per hour, they experience time slightly slower than we do on the ground. Over months in space, those microseconds add up, meaning astronauts return to Earth technically younger than if they'd stayed home. It's a tiny leap into the future, but it proves the principle: speed warps time. But what if you could take this effect to the extreme? Imagine a spaceship accelerating to near the speed of light. For the crew, a journey lasting just a few years could mean centuries pass back on Earth. They'd return to a planet where everyone they knew was long gone, effectively vaulting themselves into the distant future. Gravity can do the same trick. Stand near the edge of a black hole where gravity bends time like a rubber sheet, and you might watch the outside universe speed up like a movie on fast forward. These aren't thought experiments. GPS satellites have to account for these relativistic effects every second, or their navigation data would drift off course. Traveling to the past, however, is where things get truly mind-bending. General relativity allows for theoretical pathways called closed time-like curves, loops in spacetime that could, in principle, let you circle back to an earlier moment. Wormholes, often depicted in movies as cosmic shortcuts, might also serve as time machines if they exist. Picture a wormhole with one end near Earth and the other end racing away at near light speed. Time would pass slower for the moving end, creating a bridge between two different points in time. Step through, and you might emerge in the past, but here's the catch. Wormholes are purely hypothetical, and keeping them stable would require exotic matter with negative energy, something we've never observed. Then there's the infamous grandfather paradox. If you travel back in time and accidentally prevent your own birth, how could you have existed to make the trip in the first place? Some physicists argue that the universe might enforce consistency, making it impossible to alter past events in a way that creates contradictions. Others propose parallel timelines where every change spawns a new, alternate reality. Quantum mechanics even hints at particles interacting with their past selves, suggesting that at microscopic scales, time might not be as linear as we think. The biggest roadblock to past time travel isn't just theory, it's energy. Warping spacetime enough to create a time loop would require energies comparable to those of a collapsing star, far beyond our current technology. And even if we could muster that power, the side effects could be catastrophic. Tinkering with time might unravel causality itself, turning history into a tangled mess of conflicting events. Yet the allure of time travel persists, not just as a scientific puzzle, but as a mirror to our deepest hopes and fears. It forces us to ask, if we could revisit the past, would we fix our mistakes or create new ones? If we could leap ahead, would we find a utopia or a wasteland? For now, time travel to the past remains locked in the realm of equations and speculation. But the fact that it's even possible on paper that the universe's own rules leave the door cracked open is a reminder that reality is stranger, richer, and more mysterious than we can imagine. And who knows, somewhere in the uncharted frontiers of physics, the key to turning science fiction into science fact might already be waiting, just not quite yet. The search for extraterrestrial life isn't just about finding little green men, it's about rewriting the story of life itself. Right now, robotic explorers are digging into the rusty soil of Mars, hunting for fossils or even dormant microbes that could prove we're not alone. The Perseverance rover, trundling across Jezero crater, isn't just collecting rocks. It's looking for chemical signatures, molecules that, on Earth, would scream, life was here. Meanwhile, orbiting spacecraft like the European Space Agency's Trace gas orbiter sniff the Martian atmosphere for methane, a gas that could hint at underground microbes still chugging away. Mars may be a frozen desert today, but 3 billion years ago, it had rivers, lakes, and possibly the same primordial soup that sparked life on our own planet. But Mars isn't the only promising backyard in our solar system. 500 million miles away, Jupiter's moon Europa hides a secret beneath its icy crust, a global ocean with more liquid water than all of Earth's seas combined. Tidal forces from Jupiter's gravity keep this water sloshing, possibly fueling hydrothermal vents like those on Earth's ocean floor, where life thrives without sunlight. NASA Europa Clipper mission, launching soon, will skim the moon's surface, analyzing plumes of water vapor that occasionally erupt into space. If those plumes carry amino acids or lipids, it could be the strongest hint yet that life exists beyond Earth. Then there's Enceladus, Saturn's tiny, ice-covered moon. Cassini spacecraft data revealed geysers spewing water rich in organic compounds, including hydrogen, a potential energy source for microbes. The discovery was so shocking that scientists had to double-check their instruments. If life exists in these dark, alien oceans, it would prove that biology isn't picky. It can flourish even in the most extreme, sunless environments. Beyond our solar system, the hunt takes a different approach. Radio telescopes like the Allen Telescope Array listen for deliberate signals, cosmic hellos, from civilizations advanced enough to broadcast. SETI, the search for extraterrestrial intelligence, has scanned thousands of stars for patterns in radio noise that natural phenomena can't explain. So far, silence, but with trillions of stars in the galaxy, we've barely scratched the surface. New tools like the James Webb Space Telescope add another layer, analyzing the atmospheres of distant exoplanets for gases like oxygen or methane that could betray the presence of life. The absence of evidence isn't necessarily evidence of absence. Every sterile crater on Mars, every quiet radio scan, teaches us something. If life is rare, that makes Earth's biodiversity even more miraculous. If it's everywhere, we're on the brink of the greatest discovery in human history. Either way, the search changes us not just by revealing other worlds, but by forcing us to see our own in a new light. After all, if microbes are thriving in Europa's abyss or beneath Mars's sands, then life isn't a fluke, it's a rule, and that changes everything. Astrobiology is where science fiction meets scientific fact, a field that dares to ask not just whether we're alone, but how life might arise anywhere in the cosmos. Imagine a discipline so bold, it stitches together biology, chemistry, geology, and astronomy into a single quest to uncover the universal rules of life itself. It all starts with Earth's most unshakable survivors, extremophiles, organisms thriving in places once deemed lifeless. These microscopic pioneers flourish in boiling acidic springs, deep sea vents crushing under oceanic pressure, even the radioactive wreckage of nuclear reactors. If life can cling to existence here, in these hellish corners of our planet, why not in the methane lakes of Titan or the subterranean oceans of Europa? Yet astrobiology isn't just about hunting for Earth-like life in alien settings, it's about redefining what life could even look like. Take Saturn's moon Titan, drenched in liquid hydrocarbons instead of water. Traditional biology says life needs water, but what if Titan's chemistry dances to a different tune? Some scientists speculate about azotosomes, hypothetical cell membranes built from nitrogen compounds that could function in Titan's frigid -180°C seas. Or consider Venus, where traces of phosphine gas, a molecule often linked to biological activity, have sparked debates about microbes floating in its sulfuric acid clouds. These aren't just wild guesses, they're testable hypotheses pushing the limits of our imagination. The search extends beyond our solar system to exoplanets, where telescopes like James Webb analyze starlight filtering through distant atmospheres. Biosignatures, chemical fingerprints of life, could include oxygen paired with methane, a combination that quickly destroys itself without constant replenishment. But here's the catch: nature has fooled us before. Geological processes can mimic biological ones, producing false positives like the infamous Mars meteorite of 1996, where tiny structures initially hailed as fossilized microbes turned out to have non-biological origins. That's why astrobiologists now hunt for technosignatures too, clues like industrial pollutants or artificial megastructures that would betray an advanced civilization's presence. Perhaps the most profound shift astrobiology brings isn't just in the science, but in the philosophy. If life emerges readily across the cosmos, then Earth is a single note in a galactic symphony. If it doesn't, then we're the universe's rarest masterpiece. Either answer carries existential weight, reshaping how we see our place in the stars. And with every new extremophile discovered in Earth's harshest recesses, with every exoplanet atmosphere scrutinized for chemical anomalies, we're not just searching for aliens, we're uncovering what it truly means to be alive. The next chapter of space exploration isn't just about going farther, it's about rewriting the rules of what's possible. Take Mars, for example. NASA's Artemis program isn't just aiming for footprints on the red planet. It's laying the groundwork for something far more ambitious, a sustained human presence. Imagine pressurized habitats dotting the Martian plains, fueled by solar arrays and extracting water from the rusty soil to split into oxygen and hydrogen for breathable air and rocket fuel. Private ventures like SpaceX's Starship are betting big on this vision, with plans to transport not just astronauts but entire communities, turning science fiction into blueprints. The challenges are staggering: cosmic radiation, dust storms that last for months, and the psychological toll of isolation. But the solutions being tested today, from radiation shielding fungi to 3D printed underground shelters, could redefine off-world living. But Mars is only one destination. The Moon, long seen as a stepping stone, is becoming a hub of activity. NASA's Lunar Gateway, a small space station orbiting the Moon, will serve as a pit stop for missions deeper into the solar system, while international partners like China and Russia race to establish permanent lunar bases. The Moon's south pole, with its shadowed craters hiding billions of tons of water ice, could become a cosmic gas station, refueling ships bound for Mars or beyond. And let's not forget the commercial angle. Companies like Astrobotic are already planning lunar mining operations, extracting rare metals and helium-3, a potential fuel for future fusion reactors. Meanwhile, our robotic explorers are venturing into realms once considered unreachable. The James Webb Space Telescope, with its infrared eyes, is just the beginning. Upcoming missions like the European Space Agency's Ariel will analyze the atmospheres of thousands of exoplanets, hunting for signs of life or even industrial activity. Closer to home, probes like NASA's Dragonfly will soar through the thick, nitrogen-rich skies of Titan, sampling its organic-rich dunes for clues about how life might arise in alien chemistries. And then there's the hunt for gravitational waves. Next-generation observatories like LISA will listen for the echoes of black hole collisions so distant, they'll reveal the universe's structure in ways light never could. The real game-changer, though, might be the rise of international collaboration. The Artemis Accords, signed by over 30 nations, aim to create a framework for peaceful lunar exploration, while projects like the Square Kilometre Array telescope pool resources from dozens of countries to build the world's largest radio telescope. Even geopolitical rivals are finding common ground in space. Despite tensions on Earth, the International Space Station remains a symbol of what humanity can achieve when it works together. Yet amid all this progress, the most exciting discoveries might be the ones we can't yet predict. Every mission, every experiment carries the potential for a revelation that upends our understanding, whether it's finding microbial life in the plumes of Enceladus, stumbling upon a megastructure built by an alien civilization, or unlocking the secrets of dark matter. The future of space exploration isn't just about reaching new places. It's about becoming a species that no longer watches the stars from afar, but walks among them. And that journey starts now. As we stand beneath the vast cosmic tapestry, we've unraveled black holes bending reality, dark matter weaving invisible threads through galaxies, the tantalizing whispers of multiverses. It's humbling to realize how much remains hidden in the shadows. Every answer we've pried from the universe has cracked open a dozen new mysteries, like peeling an infinite onion where each layer reveals deeper wonders. Take dark energy, that enigmatic force accelerating the universe's expansion. We've measured its effects with staggering precision, yet its true nature slips through our fingers like stardust. Or consider quantum mechanics, where particles communicate instantaneously across light years, defying our notions of locality and time. These aren't just scientific curiosities, they're cosmic breadcrumbs leading us toward truths that could rewrite physics itself. What makes this journey so exhilarating isn't just the scale of our discoveries, it's how they reshape our understanding of existence. When the James Webb Space Telescope captures light from galaxies born just after the Big Bang, we're not just observing distant objects, we're time travelers witnessing the universe's childhood. When gravitational wave detectors like LIGO catch ripples from colliding black holes, we're feeling the very fabric of space-time tremble beneath our feet. These breakthroughs dissolve the line between humanity and the cosmos, revealing that we're not passive observers but active participants in an unfolding cosmic story. Yet for all our progress, the greatest lesson might be this: the universe resists simplicity. Just when we think we've grasped a fundamental law, some anomaly, a galaxy rotating too fast, particles entangled across space, the axis of evil in the cosmic microwave background jolts us awake to deeper complexities. It's as if the cosmos is whispering that our current theories are mere sketches compared to the masterpiece awaiting discovery. And that's what makes science so profoundly beautiful, not the illusion of final answers, but the endless pursuit of deeper questions. So where do we go from here? The next chapter lies in the hands of dreamers and doers, the engineers designing spacecraft to taste Europa's icy plumes, the physicists simulating the quantum foam of space-time, the students who'll one day point telescopes at exoplanets we've yet to name. The tools are already taking shape: quantum computers modeling alternate universes, AI sifting through petabytes of telescope data for patterns no human could spot, even nascent technologies that might one day let us touch the stars themselves. This isn't just about accumulating knowledge, it's about evolving as a species. Every time we push the boundaries of exploration, whether through a rover's wheels on Martian soil or equations scribbled on a chalkboard, we're honoring humanity's most defining trait: insatiable curiosity. The cosmos doesn't reveal its secrets easily, but that's what makes the quest worthwhile. So keep looking up, stay wonderstruck, and remember, the greatest discoveries aren't just out there in the void. They're waiting in the spark of imagination that dares to ask, what if? If today's revelations leave you breathless, just wait. The universe has only begun to surprise us. End screen prompts appear organically here, woven into closing thought. The adventure continues. Hit subscribe to join us for the next cosmic revelation, and drop your wildest space theories in the comments. Until then, keep reaching for the stars.